on like Girl Dad or something, and like somebody tells like a really funny joke or something, and this little baby laughs and she sounds like a goose, and it's really funny.
That's funny.
And I don't even remember what it's advertising
Like
anymore.
the-
I remember her laughing. It's
And
really
then there's like
funny.
those like
What is goose
sound like?
Or like,
No, they don't sound like that.
so tired right
It's
now.
like, I can't do it. It's
Did you finish yours?
Stop.
It's not good.
whenever you get like go and like this one sound.
Yeah, it's so awkward to say geese and
I think
rice.
private school like 45 on.
I don't think it's like
What
what
does
I'm
it do on
doing.
Friday?
I think you do when you.
Oh.
I don't think
I'm saying if it was doing
Can I
Friday,
talk
at least it would give us like this whole week to like get back in like the school motion, just like Wednesday. I'm like, ah!
That's really
I think we did it
Especially
better
'cause
than
Tuesday's the day before, and we're like at UBC till like 8:45.
I don't know that. Like,
Wait, we should find whoever plays Rafiki.
oh, I got the job.
Guys,
I know.
That was good.
Alexi and I said that we were gonna go somewhere.
You should come and visit me at work.
Well, we're gonna go for our own joy, but yeah, we'll go visit you.
You wanna know something? Skylar.
I'm gonna be
Because
driving.
I like trampolines.
That weekend that we have that
Or this-
competition
this
in
summer.
Minneapolis, like
When do you
This
get
summer.
and it's the weekend before spring
And
concert.
like, well, now that I found out I can get it in 180 days, not in September.
So it's like, oh yeah, back.
You commented on
Mr.
the driving.
Blind.
I said I was good.
So I went shooting this spring break. It was the coolest thing I've ever done in my life. The shooting
Training
range.
like,
Guns?
Yeah.
we went to the shooting range.
Shot a
So like,
40.
I'm going to
Like a handgun?
Yeah, handguns. And then we shot a rifle. We shot a Beretta.
Karen.
It was awesome.
Oh, Beretta's,
I
my
said
dad
and
has
I-
Beretta, and so does my
And I
Yeah.
have to work till like 5.
It's like really close to me
7:30.
actually.
Is
The
it-
where did
shooting range
you
is
go?
really
I did
close
say
to me. It's
Abby.
like right by me.
Where did you
Yeah,
go?
it's like the Coliseum. Yep.
Oh, the place that's so
I don't really like prom.
I don't know, I don't like her.
We used to go shooting all the
So I
time.
got,
I know you went
No,
to.
we used to go to a shooting range and it was indoors.
Yeah. I'm learning that I'm a rifle person, not a gun person.
You are
I'm
like,
a rifle
Yeah, it
person.
was like
I can't
really-
shoot
That's
handguns.
so like I ate them.
but the rifle, you're right.
Rifle was pretty good. Like look at the targets where it's like.
Well,
the
actually,
right
we
way.
that during work yesterday.
The right side was like, I got like around the red drop, but then like every other one I got
Last
like,
night
at
when I
least
was
two
talking
of
to
them.
Lexi.
As long as you
I was
don't
like,
really get.
it was my first time shooting.
My sister shot a Dutch
But right, but the
Now there's
pistol,
five
like,
people in there.
like,
Okay.
it was like, because the 40, I
No,
didn't think it
so I
had that much
went to
recoil,
the
because it's,
salsa from
I mean, well, it's heavy, but,
What?
yeah,
Which
it was like,
one?
and like the bullets kept flying in my face, it was like, yeah.
Oh gosh, when they like spit out of the gun.
Yeah, literally would just shoot back and like hit me right before. it was
Good
like,
goggles, right?
well, yeah, you can't go shooting without it,
Well,
yeah.
but then again, it is great.
And then we shot
I
a
don't know.
45 too.
I want to go home.
I have a load on my
45
shirt,
pistols.
but
Like,
like
I'm
I'm
And 9
shooting.
millimeter, yeah.
It's not working out for me.
You shoot
Like
like
I
a
just
James
like
Bond.
it's not working out for me.
I'm studying.
If
My
it
sister
were
shot a Desert Eagle and it literally sounded like a
We
song.
went through 300 bullets that day.
So loud.
He's probably boom.
It's crazy.
Sounds, that sounds
I'm
nice.
afraid that looks like I'm James Bond if I shot her.
It's not that bad. Like if you have it like
That's a big enough.
even if it can't.
It's like,
Yeah.
I'm gonna be there, but then I'm gonna be there.
I feel like
I'm
the
just saying because obviously we would do it together if we were with
Whenever I shot one, it
And
didn't
she
matter.
like she doesn't want to come back and be like,
Oh.
she wants to be like, no, I
What?
I'm more than
But I mean,
I'm
it's
not just stuff with a girl. So her friend's mom and she's
I would probably like go backwards from the test.
I forgot we took these.
we do tests.
I got that we took these too. Yesterday I was like, do we have math homework? Oh god. We did. I couldn't even remember.
I have to mix up.
I just
Because I started doing it, I just failed. It's a cute game.
Perchloric acid.
Great, what's I put?
You put hyper.
Oh, no, that's his writing, not my writing. It's the other one.
I have a question for number 8. I never know when to put the 3 in the front, or like when to put them aside when they're those type of problems.
So here's the, here's, I think, a way to think about it. When, I think you know what that means. This is a molecule with 2 hydrogens and 1 oxygen. So the number that's down here tells you how many of the particle to the numbers left you have. So 2 says 2 hydrogens and 1 oxygen, right? Now, when you think about a polyatomic ion, because when you mix ammonium and phosphate, you're putting those 2 ions together. You're going to need 3 of these. Treat the polyatomic ion as 1 particle. Even though it's made of 5 atoms, it sort of acts like a group of particles. So in the same way you put the number after to tell how many of the particle to the numbers left you have, you would do the same thing here. And this 3 will again tell you how many of the particle to the numbers left you have. It's kind of the same idea. So it should feel very similar because in a sense it's doing the same thing. In a sense it's different because 1 particle is made of 5 atoms and 1 particle is only made of 1, the H versus the NH4. But it's kind of the same if you view each NH4 as its own unit. And why do you put the parentheses around it? Because if you didn't, you'd have a very confusing situation. Because that looks like 43 hydrogens, right? And I don't think that's right. 1 N, 43 hydrogens, and then a P and 4. That doesn't seem right. So that's kind of the idea. In a sense, you could think of water like that. If you put a parenthesis around the H, like conceptually, it wouldn't be wrong. It would just be excessive. It would be unusual to write it like that. But even if you did write water's formula like that, I think it would be clear what was going on. So it's there's a lot of similarities. Did that help? Good. Other questions? Okay, to give you an idea, what we have left, well, I'll just talk about it. We have this week, next week, and finals week. This week, we will talk about chapters 20 and 21, which is reaction energy and kinetics. I'll do my best to explain this as simply as possible. It can be a very, very complex thing, but it's pretty simple when you look at it from the right point of view. So we'll do our best to keep it simple. Next week, and what I said would be this week, it might spill into next week, and then we'll finish up with a section of radioactivity, which is kind of fun stuff. Mary Curie was one of the first people to discover radioactivity. Died for her services due to the fact that radioactive substances are cancer causing. Nobody knew that at the time. I'm not even sure if we knew what cancer was, but it ended up shortening her life and the lives of her fellow researchers, actually, around the turn of the century. So we'll talk about that, and then that's it, and then we'll get ready for a final. So if I'm speculating, probably next Tuesday, we'll have a quiz on what we talk about this week, and probably the following Tuesday, we'll have a quiz on radioactivity. That's speculation, but that's probably pretty close. And now, next Tuesday would put us here on the calendar. That's gonna be the first quiz. The following Tuesday would be the week of finals week, and you might say, oh my gosh, Mr. Fly, having a quiz the week of finals week, how inhumane. Well, you're gonna have to know everything for the final anyways. It's gonna be nice to have some feedback before you jump into the final. So, having some feedback on radioactivity, I think, will be nice. Since you'll be preparing for the whole semester's worth of work anyways. And when you look at the semester worth of work, this is going to go back to chapter 10. So this is just for your information. When you look at where we started for the final, chapter 10, and we went from chapter 10 straight through 10, 11, 12, 13, 14, 15, 16. Yep, we skipped 17, 18. Okay, so 10 through 16, 20, 21, and then I think it's 31. So this has been covered, and this is to be covered. And that's what the final is going to be over. So if you wanted to start reviewing, just even a basic review would probably be to your benefit. I'm sure you've noticed this yourself whenever you study, but if you have a lot of stuff to study in one night and you try to put it all together, it's challenging. Does anybody notice this?
Doesn't really go too well.
You say what?
Doesn't really go too well.
It doesn't go too well? Yeah, it wouldn't go as well as doing it in bite-sized chunks. You probably, I'm guessing that whenever you were a little baby and you started saying your first words, well, there may have been a challenge there. I suspect it was easier to start word by word than just blurting out sentences. If you think about that, right? The learning process is naturally in bite-sized chunks. I don't think many of us as children just started blurting out full sentences. Is that true? We probably started with like mama, dada, like whatever other word that you learned first. Does anybody know their first word?
I do.
What was it?
It's not appropriate to say in school.
Okay, well, that's interesting. Anybody else know their first word?
Mine was mama.
Mine was mama.
Okay, so yeah, so we started simple. We weren't like, mama, go get the such and such, right? So think of that the same way as you're preparing for the final. If you try to put it all together in one night, it will be significantly more challenging than if you take it in bite-sized chunks. And even if all you do is, during your break period, take 5 minutes and just flip through your notebook, now, today, tomorrow, the next day, you'll find that it'll be more familiar whenever you look at it later. So that's my suggestion. But in the meantime, let's get out our notebooks and let's get cracking on the next section. So the section here, 20, deals with reaction energy and reaction kinetics. It is possible to look at any substance, which is what we do in chemistry, we study substances. It is possible to look at any substance and look at the energy that is contained within that substance. Gasoline, for example, would be a very energy-rich substance. I mean, if you really get down to it, you fill up a gas tank with 15 gallons of fuel. I mean, think about what 15 gallons would look like. You've probably seen a gallon of milk before. Imagine 15 of those. That can move a car that weighs 3,000 pounds, 400 miles down the road. That could take a car from here to Louisville, Kentucky. That's kind of impressive, right? To think about. 15 gallons of fuel. 15 gallons of water would have less energy than 15 gallons of fuel. 15 gallons of gasoline. So we could talk about energy. And the word kinetics, does that mean anything to anyone? What were you saying?
Like touch, feeling?
Oh
no, is that like?
Yes, I mean, there could be touch involved in kinetics, but
It's the same word though.
it is the same word. Kinesthetic, does anybody know where that word is often used? If we talk about the word kinesthetic? So learning style, yeah, there's visual, auditory, kinesthetic are the three primarily referred to learning styles. And kinesthetic refers to people who learn, yeah, through action.
It's like mu.
Through action.
Mu K.
So kinetics involve
It's like
motion,
yeah.
movement,
Friction.
Yeah.
and there is a movement to chemical reactions. There's two substances interacting with other substances, and through those interactions you get potentially chemical reactions occurring. So, motion is a necessary part of a chemical reaction. You can't have two substances interact with each other if they're not moving to touch one another, moving to get near one another. So touch would potentially have something to do with it. And we have a concept of energy, I think generally speaking. So when you look at all reactions and you look at reaction energy, there are basically two types of chemical reactions. By the standard of energy. Basically two types when you look at reactions based on their energy. One, exothermic, and the other, endothermic. Looking at the words exothermic, endothermic, any root words that you notice being familiar? Mm-hmm.
Is like endo or exo is like outside, like exoskeleton, and then endo is like internal.
Mm-hmm.
So,
Mm-hmm. Holly's got that one down. So exo means outside, endo means inside. And thermic, any word you see there?
temperature.
Heat, temperature, yeah, like a thermometer, a thermos, thermostat, yeah, great. So exothermic means heat to the outside. Exothermic reactions are reactions that give off heat. Can you think of a chemical reaction that would give off heat?
Atomic bomb.
Great.
Okay.
Another one? That's the very,
It's a ginormous scale.
it's a, if you've been listening to the news, that's a relevant topic of discussion for a social studies class if you're talking about current events, because North Korea is, has 2 nukes on missile launchers right now,
Just figure this out.
currently. And they might be launching them to South Korea, they might be launching them to Japan, they might be launching them to the US. If they try to launch them to the US, they won't make it, they'll get to like halfway across the ocean, but, yeah.
They kind of scaled it up, it's kind of funny.
It's still terrifying to think that there's nuclear missiles on launchers with a dictator who's younger than me. I think he's 28,
Yep.
and he's
It's really
He's
short.
crazy.
It's just
he's
round.
he's
Yeah,
been from a long line of dictators. So imagine 25 years old running a country where everybody did what you said, because that's what a dictator is, right? Dictator, like you dictate what happens, yeah? So they listen to what you say, and that's nerve-wracking. Atomic bombs, yes, would give off heat. Anything else? Any other reactions that would give off heat?
Fire.
Burning wood, anything on fire?
Furnace?
Absolutely. So, exothermic give off heat. Heat to the outside, that's heat being given off to the outside. You can feel the heat. If there's a fire, you can feel the heat. If there's an atomic bomb, or frankly, any kind of bomb, I would assume. Well, except maybe they have bombs that just send out an electrical impulse and take out all of the,
EMPs?
what are they called?
What do we call EMPs?
Yeah, electromagnetic pulses.
Yeah.
They send out an electromagnetic pulse which cuts out all the power, all the internet, all the electronic gadgets and gadgets.
No one really knows you.
That could, yeah, drop that in New York City, that would have a pretty
So that
tragic
makes
effect.
So, okay.
Endothermic, on the other hand, are ones that take on heat on the inside, so they sort of like absorb heat. If you don't give off heat, you're taking heat on, so we could say these guys absorb heat. Now, this may seem counterintuitive, but let's make a graph of an exothermic reaction, graphing the energy over time.
Yo.
Now, any chemical reaction is going to take time, whether it be the atomic bomb example or whether it be the light the wood on fire example. In either case, there's going to be some elapse of time. And when we look at the actual chemical components that are in the chemical reaction, if we're giving off heat, consider what you start with, the reactants, and consider what you end with, the products. So, in an atomic bomb, we start with whatever's inside the atomic bomb, and we end with an exploded bomb that's probably practically useless. Agreed? So, if you think about this, the atomic bomb itself has so much energy that it's terrifying, right? So the energy is very high. Normally, to get any reaction going, because if you think the atomic bomb is just sitting there, is the atomic bomb going to go off by itself? I hope not. That would be, yeah, that would be a bad idea. I think if we made an atomic bomb that would go off spontaneously, that would be a bad idea. Normally speaking, there's some amount of energy that's required to get the reaction going. Like you have to hit the detonate button, or, well, if you hit the detonate button, there's going to have to be something that's happening inside the bomb to get that happening. And so, as a result, there has to be some amount of energy to get the thing going. But once the thing goes, it's going to give off a lot of energy, and what's going to result is going to have less energy than what you started with. The atomic bomb has so much energy, it's frightening. Once the bomb goes off, though, what's left is, I mean, from a chemically speaking, the amount of energy that it has very little. The energy's been given off to the environment. So this is the energy of the chemicals that you start with. This would be, if we would put here, this would be the energy of the reactants. Those are the things that you start with. And down here is the energy of the products. Now we could, if we wanted to, measure the amount of energy that was given off between the reactants and the products. And in this case, there's an energy loss, because the substance gives off its energy, it's losing its energy, giving off its energy to the environment. Well, in any rate, when we look at the change in energy, that's called delta H. You could think of that as change in heat, although that's technically not what delta H is. When we talk about delta H, that's the change in enthalpy. Enthalpy is a fancy word for heat, so I'll put heat out here in parentheses. But know that when you see change in H, it's change in enthalpy. Think of it as heat. So there's a change in heat when you look at the energy of the reactants and the energy of the products, or the energy given off. In the case of an exothermic reaction, we could say the change in H here is, that's ENTHALPY, by the way. We could say that delta H is less than 0. In other words, the delta H is negative. Let me just write that. That'll be, then you don't have to do the mathematical translation. delta H is negative. Why? Because we lost heat. From where we started to where we went off, we gave off energy. Now, there's this little bit of energy here that was required to get the reaction going. That's called the activation energy. The energy that's required to activate the reaction. Not all reactions have activation energies. Not all reactions require something to be done, require energy to be given to the situation for the reaction to be going. Some reactions are spontaneous. Think of Alka-Seltzer in water. When you put the Alka-Seltzer in water, you don't have to stir it, you don't have to heat it up, you don't have to do anything to it. The reaction will happen spontaneously. When you have the atomic bomb, the reaction should not happen spontaneously. Right? When you have the log, it should not light on fire spontaneously. You should have to heat the log up to a certain temperature, but once you do, the log is not only going to give you back the temperature you gave it, but give you back a whole lot more. Make sense? Okay, now, an endothermic reaction, a reaction that would absorb heat. Now, think exothermic give off heat, you could feel the heat from this. An endothermic reaction, the item would, over time, feel colder because it is taking on energy. This would be the opposite reaction. If we look at this energy over time, what we start with is going to be very low energy, and what we end with is going to be very high energy. So initially, we have very low energy reactants, and finally, we have very high energy products. We've absorbed heat, we've absorbed energy. And if we absorb the heat, we're taking the heat from the surroundings would get colder. These reactions would feel cold to the touch. Now, if you compare the energy of what you end with the energy of what you start with, there is also going to be a change in energy, a change in enthalpy. You could think of it as a change in heat. And in this case, the change in energy is going to be positive, because what you end with has more energy than what you started with. What you are dealing with, the substances you're dealing with, have taken on energy, and they're now more, they have more energy. The delta H is an increase along the graph. And if you're looking at this graph to try to find the activation energy, let me make sure I have this right. The activation energy is this whole bit there, because to get this reaction going, you're going to have to heat the substance up all the way to this point just to get it to go through the reaction. So here, that big amount of energy is the energy required to activate the reaction. Let me give you an example. C plus O2 yields CO2. This has a delta H value of -94 kilocalories.